welcome to this, the year's last webinar. And this is a really interesting one because it's on OPTUM G3. And this is going to be quite an amazing presentation, I believe, because it's going to be 3D geotechnical design running in real time here. So I know Kristian has been looking forward to this, right, Kristian? Yeah. Another, just a small, actually a very big thing, because today is a great day. It's a very great day because we have just released a new program called OPTUM MP, which you can see here on the web page Kristian is showing. And this is actually, we've been fighting like crazy to get this ready before Christmas because we decided to give this out for free. And so this is kind of like a Christmas present, right? From OPTUM to all you guys. And it's a funny story because when I don't know how funny it is, but when we started out some 10 years ago on this journey, we actually wanted to make the very first program for designing concrete slabs. And then certain things happened along the way, and we decided to go into geotech instead. But we've had this on our minds all the time, and actually concrete slabs is already part of OPTUM G3. But we decided to make a completely dedicated program for design of reinforced concrete slabs. And I just encourage you guys to go in and check it out. Download it, it's completely free. And be sure to spread the word. If you have any of your colleagues who's interested in this, or you are interested in it yourself, then please feel free to promote it in any way you can. So is there anything you want to add, Kristian, to this OPTUM MP?
No, I think you covered it all, Jan. So.
All right, fantastic. Okay, then the format is the same as usual. So a 30-minute presentation followed by a 30-minute Q&A session. Remember, there is a Q&A button at the bottom of your screen for asking questions. We'll be recording this as usual and sending out an update after the webinar has been done. And so that's all for me. Kristian, please start the presentation.
Yeah, thanks, Jan. I can just see my, sorry, bear with me. My microphone has just gone a little bit. Is that
me?
Okay, great. Great. So, yeah, thanks for joining. And so this presentation was meant, or this webinar was meant to be just a brief introduction to 3D analysis using OPTUM G3. We've had webinars on particular applications in the past, and we'll continue with that. And there's, of course, lots of particular 3D applications that we'll also cover in the future. So this is just meant as just a very brief and basic introduction to 3D analysis using OPTUM G3. And a brief outline of what I'll cover, a very short introduction. Then I'll say something about finite elements, which is kind of important and which is one of the things that really sets G3 apart from other similar programs. And then move into applications and foundations and monopiles, bearing capacity and deformation, so ULS and SLS. So 3D analysis, and sometimes people say, what's the big deal with 3D? Because it's just the same as 2D, just 3D. And so for 2D, we have OPTUM G2. For 3D, we have OPTUM G3. And that's, of course, one way of looking at it. But I think anyone who's done any serious 3D analysis knows that everything is more painful once you move from 2D into 3D. The definition of geometry is an issue often, much longer run times. And there are also some issues potentially with finite elements. The types of elements we use in 2D don't necessarily carry over in a particularly straightforward manner to 3D. So the purpose of OPTUM G3 is to alleviate these pains by, first of all, allowing for an easy definition of geometry, and then by supplying some efficient and robust computational strategies, and accurate and reliable finite elements is very much part of that. So with finite elements, what we have in 2D, we have various elements in 2D, and one of them is this 6-node triangle. So it has a quadratic interpolation of the displacements, and that can be generalized very easily to 3D in the form of a 10-node tetrahedron. So we know that the 6-node triangle, it's widely used. It's a good and reliable element. Some people say we should use 15-node elements. That's available in G2 as well. I tend to recommend the 6-node element for things like elastoplastic and consolidation and those types of analysis. For limit analysis and strength reduction, we of course have the upper and lower bounds, but for all other sort of analysis, this is a good and reliable general purpose element. If you actually compare accuracy versus computational time, this is what you really should be comparing. The 6 and 15 node triangles are more or less the same. And you would think then that since this is a pretty good element, then that the 3D analog would have more or less the same properties. So it has as well a quadratic displacement interpolation. It's widely used. I believe it's the only element available in Plaxis 3D. But it turns out that the kind of nice properties of 2D do not at all carry over into 3D. This element suffers from what is known as volumetric locking, which is a phenomenon that really kicks in once you're dealing with models that imply zero change in volume. So for example, Tresca type materials where you have no dilation, or if you're running analysis with a Poisson's ratio close to 0.5, then you will experience this volumetric locking, which basically means that your response is going to be far too stiff, and your ultimate limit state is going to be your bearing capacity, say if it's a foundation you're looking at, is going to be far too high, sometimes even infinite. You don't even reach a limit load. This is something funny enough, and sort of to make matters worse, that gets worse as the number of elements in the mesh increases. So it's not something you can get rid of just by increasing the number of elements. And what really makes this funny, even though this element is widely used, it is actually also at the same time well known that it's a really poor element, as this article, Nachtigall, Parks and Rice, 1974, which is sort of a famous article which describes this element and the bad properties of it in detail. So what have we done in G3? Well, in G3, we also use a 10-node tetrahedron, but it's a 10-node tetrahedron with some enhancements, you can say. First of all, we have separate interpolations for the stresses and the displacements, as opposed to just the displacements as in conventional FE. And that means it's very easy to introduce various enhancements. Among them, there's what is known as the enhanced assumed strain approach to basically avoid volumetric locking. So I can't go too much into detail about it here, but I can just say this is a great element, and it has, in terms of computational cost, it's the same as the basic 10-node tetrahedron. So this is an important point in terms of actually obtaining reliable results. And just sort of to test the element, a bearing capacity of an undrained circular footing on a Tresca material, and there's 1/4 of the model here, 10-node elements used. The error in the exact solution is this one here. I computed it using Chris Martin's APC. So the error for the standard element and this mixed G3 element versus the number of elements. And you can see the standard element really performs very, very poorly. And you can see the error increases as we increase the number of elements, then it decreases a little bit and then becomes infinite. So basically the limit load is infinite. We never reach a limit load, whereas the mixed element performs really quite well, as you would sort of want or even maybe hope for. It's really quite good. Mean stress fields at failure. The standard element looks terrible. Something is clearly wrong here. The mixed element looks a lot more credible. So, so what I would now do is I would like to just sort of move into the applications. And the first application I was going to consider is the bearing capacity of or also deformations, but a circular foundation on a layered soil. So this is in G2. You can see the sort of, I'm in axis symmetry mode here. So I have a layered soil. This is sand up here, friction angle of 35 degrees, and this is clay, an SU of 100 kPa. This is 2 meters. This is 5 meters, and the footing has a radius of 1 meter and a depth of 1 meter as well. So, and I have limit loads. I've calculated upper and lower bounds. So a lower bound of 1201 and an upper bound of 1233. So an exact solution of about, say, 1215 or so. And this is the strain field at collapse, and you can see it looks sort of like that. I've used adaptive meshing, of course. So I'm now going to set this problem up in G3, and so this is what you'll see when you open G3. Actually, you're going to be greeted by a welcome screen where there's some videos, and that might be useful, and also on our YouTube channel. There's also a lot of, or some at least, tutorial videos. So this here is 10 meters by 7 meters. So I'm going to now draw and that's a cylinder, of course. We want to define the soil domain, and I'm going to use this N prism here, which is a discrete cylinder with a certain number N sides. And so the default is 12. Let's just stick with that. And then a radius of 10 meters and a height of 7. And then basically on top of that, I'm going to create an identical one, again with a radius of 10, and now with a height of -2 meters. So a height of 2 meters, but extruded downwards. So to basically create the 2 layers. And then the foundation, and at the center, and a radius of 1 and a height of -1. So here I have my geometry. I can make this transparent so you can see here is where the footing sits in the ground. And then G2 follows the scheme, the general scheme or G3 follows the general scheme of G2. So geometry, so there's various tools for that. And then materials, and this is what I need up here is this medium sand with 35 degrees. That can of course be edited. And then a Tresca which has the right SU in this case. And then a rigid material for the foundation, exactly as I have in 2D. And then we move on to standard fixities. Again, that is completely analogous to what we have in 2D. And then finally, we need I would like some uniformly distributed load on top of the foundation. In order to apply that, I first need to untick solid selection. So now I'm only selecting faces, lines, and points. So I can select this face and move to features, and then apply a multiplier distributed load. And that is a distributed load over the foundation. And then I am ready to run my limit analysis. Again, following G2, we have the stage manager, element type, and we have 3 elements in G2, lower, upper, and mixed. I'm only going to be using the mixed today. That tends really to be really quite accurate, but you can of course use the upper and lower bound elements as well, just as in 2D. And I'm using 3 adaptivity iterations, starting from 1,000 elements, ending up with 1,000 elements as well. That's really not a lot of elements if you compare to what we have, of course, in 2D here, right? We have, this is 10,000 elements with an adapted mesh for a 2D slice of the problem, and now we're using 1,000 elements for the full 3D problem. We could, of course, have utilized symmetry in this case and so on, but I just wanted to just sort of set up the full problem, and then as an exercise, I think you always want to do that whenever you start using a new program, to just make sure that it gives reasonable results. And it was also just to show that this element really is quite accurate, this mixed element. So we have a collapse multiplier of 1189, let's say, and the exact we decided was about 1215. So we could, I think I have MATLAB here. So 12, we could calculate the error, minus 1189 divided by 1215 times 100%. So an error here of 2% for a very coarse mesh. And this is really not unusual for this mixed element. It tends to really provide very, very good solutions, even for relatively coarse meshes. So, and this is how things collapse. You can take some clips through this, and we have something now that kind of looks, you can see there's a bit of a rotation here of the foundation, which of course we don't have in the 2D model. If we plot the strains, we can see that, of course, this is a much coarser mesh, but we can see that definitely the collapse mechanism sort of dips down into the clay layer, just as we had in 2D here. So we have the clay layer activated. So that's how that works. You can then ask yourselves, well, how about inclined loading? And that's of course something that can be done as well. And in order to do that, I think it's more convenient to really work with a point force right at the center of the foundation. That's what I prefer to do anyway. So I'm going to apply that. That can't be applied to solids directly, just as in 2D, these multiplier concentrated can only be applied to structural elements and not solids. So it's exactly the same in 3D. And so we need a structural element. In 2D, it would be a plate. In 3D, it's a shell. So it's a rigid shell, analogous to the rigid plate in 2D. It doesn't have to be rigid, but it can be anything, elastic, elastoplastic. But let's just make it rigid in this case. That's what we want. And then I'm going to just do sort of a top view, because what I'm going to do is draw a cross on this cylinder to basically have a point defined at the center of the cylinder, so that I can apply my point load like that. And let me just rerun this. This of course should give me the same result as before, but just with the area of the foundation multiplied on. But the advantage here is that I can then start playing around with an inclination. So this is of course the types of load you get typically from, let's say, the structural engineers. They supply a set of reactions, and they can be applied really quite easily without any conversion into distributed loads and so on. So that is pretty convenient. Now, and we're done. Now a load then of 3579. And again, it looks as before. Now, what I wanted to do was not exactly give this an inclination, but apply a limit load of 3579. And if I run, or a multiplier load of 3579, the limit load. So if I run a limit analysis now, I'll get a load multiplier of 1. But what I'm going to do before I do that is include a fixed point load and say 500 in the X direction. So 500 horizontally. And then what is my limit load now? It'll be less than 1. It'll be some value which is kind of equivalent, you could say, to the inclination factor that is used in most codes. So there's going to be a decrease in the vertical capacity as a result of having, of course, a horizontal force component. So that effectively we have an inclined load. And let's see what that multiplier is. Yeah, so it's slightly above, slightly below 1. First stab here, well, it is actually slightly above 1. In this case, it converges from above, and we get a let's say, an inclination factor or load multiplier of 0.86. And if you look at the deformation mechanism, yeah, it kind of looks as expected as well. Now, and you can apply moments as well. So the way it works in G3 is that moments are to be applied about a line. So for example, this line here, and you would then have a fixed line load. That fixed line load has X, Y, and Z components, but it also has a moment component, as you can see here. So you can now, I think you can see these round arrows. You can probably see it a bit better if I remove this one. So these round arrows here, which are moments. So so that's how that works. Now, just quickly, I wanted to do a deformation analysis. So let me just get rid of these forces here. And then what we do in a deformation analysis, again, this is kind of analogous to what we do in G2. We would first want to calculate the initial stresses. So we have the usual initial stress analysis so that the initial stresses are calculated in accordance with the earth pressure coefficient K0 at rest. And then once we have the initial stresses, well, then we can do elastoplastic analysis where we start loading the foundation up. So let's apply a load here of, say, 500. And then another stage where we ramp the load up to 1000. Now, and then we simply run. So a sequence of linked stages, just as in 2D. This type of analysis here, if you want to compute a full load displacement curve, that can of course be done, and can be done by increasing the number of load steps, or it can be done in a sequence of stages, which is often the way I prefer to do it, actually. And if you do it like that, then it is really useful to use the scripting interface that we've developed to go with G3 as well. So we have a scripting interface that allows you to kind of take charge of the program without actually having to define everything manually through the user interface with the mouse and so on. So it's very easy to set up how many ever stages you want, 20 or 50 or 100, and then just run it rather than having to do it manually as I've done here. For a couple of stages, the manual approach is of course fine, but if you want more than that, then the scripting interface is a good option. I won't say anything about it today because it's kind of a big topic in itself, but we'll run another webinar after Christmas on this scripting interface. And so that's the analysis, and let's look at the final deformations, and that looks something like that. Looks a bit weird. It kind of looks a bit like a trampoline. So the soil sticks to the foundation, which of course is not completely reasonable because the soil here is sand, so you wouldn't really think, but that's of course, that's how finite elements are. So what we really should have done, and what I'm just going to do for the last stage here, what we really should have done is we should have included some interfaces on this foundation. So if I hide these solids, then I have access to the foundation itself, and I can then select the faces of the foundation and then apply interfaces, or as we call them in Optum, shear joints. And the material in these shear joints is the soil material itself. You could of course have included some other material with a lower friction angle if you had wanted to do that, but let's just say there's no reduction in strength. And then let's just try to run this last stage again and see if it doesn't look a bit more reasonable than this sort of bouncing trampoline. Yeah, this runs a little bit slow. I think my video takes up a lot of CPU on this relatively old computer here that I'm using. Yeah, so the displacement has increased a little bit as well. And let's see how it looks. Yeah, so that looks a lot more reasonable. The foundation detaches clearly from the soil. So so that's foundations. And then the last example, let me just save this. Then the last example, or the second example I wanted to just set up is one that there's been a lot of interest for, and that is a monopile. So it's a 20-meter monopile with a penetration of 10 meters, and then there's 10 meters above ground. And then the question is, what is the capacity? What is the horizontal capacity for a force up here at the top of the pile? This is a Tresca material SU of 100 kPa, just to have something that's not completely unrealistic. And so that's the task. It has a width or a diameter, the pile of 1 meter. And so to set up that problem, I'm going to just start a new problem. Again, we need a sort of a circular soil domain, and 12 should be okay for that. And then I'm going to give it a radius of 20, height of 15. And then I'm going to define the pile. We could use a few more sides on that. And the top of the pile is 10 meters above ground level. The radius is 0.5, and then the height is minus 20. So here we have the soil and the that's not what I want to do. I want to make it transparent, the pile within the soil. And then, as I've indicated here, we can utilize symmetry. And the way to get rid of half of the problem is to draw a box that intersects like that. And then basically we have the intersections created automatically, and we can then start deleting what we don't need. Then for materials, this is a Tresca, and this is Tresca as well. And so a monopile is a sort of a hollow steel cylinder. And this part up here is not exactly hollow, it's a solid, but we can then, by right-clicking, delete the interior. And then if we delete this face here, we have this hollow shell that we want. And we can then start applying shell elements. Just need to be a bit careful. I don't want select them all except, okay. Shell, and then I put a few too many, but they can just be deleted again. This one shouldn't be there either. And at the bottom, it's open. So a thin shell in a soil. And again, I've used here a rigid shell because I'm only interested in capacity. If you would be interested in deformations, of course, you would use either an elastic or potentially even an elastoplastic shell. But for the purpose of this little demonstration, a rigid shell is fine. Then an important point is the interfaces between the soil and the pile. You can see these sort of dashed lines here, possibly. That's the interfaces. So the shell elements come with interfaces automatically. And the material at these interfaces is the same as the surrounding soil material, which is not exactly what we want. We want a soil with the same underage shear strength as the surrounding material, but we want to have a tension cutoff. So we want to basically eliminate the possibility of having tension between the pile and the soil. So I create a duplicate of the soil material. That's the one here. And it has exactly the same properties, except that it has a tension cutoff, yes. And I then need to apply that material to the interfaces here. And that works exactly, again, as in 2D. We have these plus minus interfaces and apply the material. And we are then almost set up. We just need some boundary conditions, some support, standard fixities. And then we also need symmetry conditions for the pile, and that those conditions correspond to the pile being supported out of the plane and also restrained against rotation about these two lines that I've selected here. So that's call it a plate BC, that's what it's called in 2D as well. And then free in the X and Z direction so that it is only supported out of the plane. And then let's just use a distributed load. I could have done as I did before with a line and a point load, but a distributed load will be all right in this case, I think. And then let's use, in this case, let's go to 2000 elements to just have a few more than what we had before. Yeah, this is how a problem like this would be set up, and I especially have to emphasize the importance of the interfaces here. So let's see if they are active. One difference between G2 and G3 is that that the results come in as these adaptive iterations progress. In G2, everything comes in at the end. Here you actually see the progression of the adaptivity. So this is the first unadapted mesh with 1,000 elements, and here we have the capacity, and we can plot it like this as well, and you can see that the pile turns over like this, and we have a nice separation between the soil and the pile down here. So due to this zero tension interface. Let's plot some strains, and that is kind of defines a familiar pattern as well. We have the shear strength mobilized in front of the pile, and then here down at the back of the pile at some depth. And let's have the last iteration. Oh. All right, so that's how it looks, and yeah, let's just have this slip line slightly more well defined. So this type of pattern here, which is sort of typically what you see for these types of piles. All right, so that's basically what I wanted to say, and there's a lot more to it, of course, but it was just to give you a bit of a feel for the types of problems that can be solved, and I think it's fair to say can be solved without too many complications. So if there are any questions, I will now have a look at the questions. So first question, can I give some more details on the upper and lower bound elements? That's going to be a bit difficult for me to give that here because it's a fairly long story, but the basic premise, of course, of the upper and lower bound elements, which are available by selection. So in G2, we have a whole range of elements, upper, lower, and a whole range of others. G3, only 3. Lower bound, upper bound, and mixed. So the lower and upper bounds give upper and lower and upper bounds respectively to the exact solution, and the mixed element then is somewhere in between. The mixed element can be proven mathematically to always give a solution that's in between the upper and lower bound elements for a given mesh. So for that reason, I tend to use the mixed elements a lot because it's of course in that area between the upper and lower bounds that the exact solution is to be found, and the mixed element has a tendency really to hone in on that very quickly. But the details of the elements, other than say that they provide upper and lower bounds, you're very welcome to get in touch with us, and then we can discuss further. But the exact details of it, I don't think I'm not really prepared to talk about that, and it's a kind of a lengthy explanation. There is, though, in the G2 theory manual, it explains it with respect to 2D, but the basic principles are exactly the same in 3D. So can Optum G3 calculate the vertical capacity of the pile? Yes, absolutely. It's just simply a question of changing the direction of the load. So having it vertical instead of horizontal, and you'll get the vertical capacity of the pile. The vertical capacity of this monopile is not going to be very high because it could actually sort of determine it analytically, right? Because it's pretty much this pile just working by skin friction. But yes, that can be done, or an inclined load, or some sort of moment, or whatever. Any load combination can be accommodated. What would be a correct way to simulate soil interaction? So screw pile with the plugged soil. I'm not really sure about this question. A screw pile is something that can be modeled. I mean, you can make various approximations to the geometry. You can model sort of a rod with some blades, with some circular blades, or you can import the exact geometry. We're actually doing that at the moment with exactly for a screw pile, where we have been supplied by or will be supplied in the very near future with the exact geometry in some sort of CAD format, IGES. Jan knows a lot more about this than I. So, but we have the possibility to import CAD data using various sort of the well-known formats, import the data into G3, and then apply materials and supports and loads and so on, and then run the problem. So I don't know actually, and the reason that's of interest to us is I don't know of anyone who's actually modeled a real screw pile before. So in principle, it's not difficult, right? But you need the geometry, and if you have that, then I think the rest should be pretty straightforward. So we will see about that. Again, if you get in touch with us, then we can keep you in the loop regarding how it's going. Why don't you have an interface at the bottom of the pile? Well, this is an open-ended pile. This is just basically a cylindrical tube, a steel tube. So the bottom here is open. That's of course convenient in terms of installation of piles like this. So that's the reason. The thickness of the pile, yes, absolutely, that can be modified. Now, I'm not completely sure what is meant by thickness here, because this is a shell element. So from a geometric point of view, the thickness is 0. And we're dealing with a rigid shell, so it's not really, the capacity of the shell is never really exceeded. But you could have gone for a, say, an elastoplastic. Let me just duplicate that one. You could have gone for an elastoplastic shell where there's the Young's, all the elastic parameters, the moment of inertia, and the sectional area, which is sort of the same as the thickness. So yes, that can be modified in that way, in the same way as you modify the thickness or the depth of a beam from a geometric point of view. It has no extent, but of course it does have a height and a width and so on. And it's the same with the shell here. Or if you have a very thick shell, you could model it as a solid as well. That might, under some circumstances, be justified. So vertical load only, and then the issue with the bottom plate there that's missing, that will of course really not be a good thing for the vertical capacity. So this is a monopile, an open steel tube. You could have easily, it would have been quite actually a bit easier or a lot easier to model just a solid pile using just solid elements, so concrete pile or something like that. So that can definitely be done. So yeah, MC should be mandatory, and Hook-Brown too. I agree with the first one, and the more Coulomb model is available. Hook-Brown is not available at the moment, but it will be soon. That's what I can say about that, as well as the GSK model that is available in G2, which is a kind of similar to Hook-Brown, but in many ways a bit better. Then there's a question: what about material? What about variation of strength with depth? Yes, and that again follows the G2 scheme of things. So any parameter can be prescribed to vary with depth or with the spatial coordinate in one way or another. So you press this, you select the parameter you want to vary, and then P for parameter, and then of course there's the constant, that's the most basic. Then you have a gradient where you have a value at some reference Z value, at some reference depth coordinate, and then at the gradient. Or you can have a profile as well, that's useful as well. So the Z coordinate and then the value of the parameter to basically define any profile, an undrained shear strength profile with a crust or whatever you want, can be done in that way. Could use a program to simulate stone columns. I would say so. I would say so. I'm not sure what the properties of a stone column really would be. If it would be reasonable to model that as a rigid material or some sort of frictional material, but I would say definitely yes. Either way, that can be done. Then there's a question on thermal coupling, and no, thermal coupling is not included, and it's not something we are planning to include anytime soon, to be perfectly honest. I don't think, yeah, well, who knows, but it's definitely not available at the moment. And then there is another question on modeling tunnels or pipes, and then can the program capture the gap at the interface? And I think that the answer to that question is yes, and that's the gap we see open up here with the pile, right? So we have this gap between the soil and the pile, and that's of course extremely important for these types of problems here, as well as for many other problems, to really have the correct interfaces, to not have the soil stick to the pile here. And it's the same kind of thing with the pipeline. So so yes, these interfaces, as I kind of hope I showed, can be included really quite easily. So it's an interesting question. If you simulate geogrids using a shell type element and in an elastoplastic setting taking into account strength, will you have to enter the moment of inertia and the area as equal to 0? And the answer to that question is kind of yes. Now 0 is kind of an ugly number for a moment of inertia, so you might want to experiment with a small value, but of course a geogrid has next to no bending stiffness and doesn't really have any bending strength either, so you would also have to set the yield moment. If you're just talking about strength, what you could possibly use would be a rigid plastic shell where you have a yield moment, so that would be some very small number, and then you have a yield strength, so the tensile strength of the of this membrane, of this geogrid, of this shell, and set that to an appropriate value. And then there's the area as well, the sectional area, or if you like, the thickness of your sheet, so that the sectional area times the yield strength gives your force per meter of geogrid. So I'm quite confident that geogrids could be modeled in that way. That should not pose any problems. Yeah. Then there is a question, an interesting question as well. I think we just have time for that. What about suction anchors? And suction anchors is an interesting application that we have looked a bit at as well, or at least I know the program has been let's just save this, has been used for that. And what is a suction anchor? Well, a suction anchor is kind of an inverted bucket that you insert into the ground. So if we again have a soil domain, which looks maybe something like this, and we then have our suction anchor. Let's say a radius of, again, 0.5, and then a height, let's say -4. So we have this bucket, this inverted bucket inserted into the ground, or into the seabed, if you like. And so let's say that this seabed is a Tresca material, and let's again just cut half of the domain off like that, and then we would apply some shell elements, and again it's an open bucket. So this bucket is inserted into the ground, and then the idea is that you can sort of anchor some sort of structure to this bucket, so that we would have, say, a horizontal force acting somewhere, let's say halfway down the anchor. So I need a point down there, something like that. So same radius, and then a height of, say, -2. So that gives me the point I want, namely this one here, that I can then apply a multiplier load to, and that could be made a vertical load. So this is a suction anchor or a suction pile. And then the question is, what is the capacity of this? And And also another question is, of course, what is the optimal point at which the force should attack? Is it midway down? Is it further up? Is it further down? You can play around with that, of course, in a sequence of analysis. So yeah, here I actually forgot to include the interfaces now. So things are going to look kind of interesting. Again, let's plot some strains, and then you can see that we do not have this gap opening up. So you have to be a bit careful, because the shear strength of this interface is exceeded. But as you can see, the soil follows the pile, the soil sticks to the pile. And that's, of course, what we would rather not have happen. So if the soil has enough strength to stand up by itself when we move the pile and leave some sort of cavity behind, then of course this should not happen. And it's kind of interesting to see what the effect of that will actually be. So let me just create an interface material again, duplicate that, and then say the attention color of yes. And I always like to color it in some sort of a bright green color, so I can see that it's actually been applied. So that was our solution here, without interfaces. So with full tension at all interfaces, you can see it looks sort of like that. Shear dissipation is another good quantity to look at. It's basically the shear stress times the shear strain. And you can see it looks kind of, well, it's a symmetric mechanism. And then if we apply these interfaces, these proper interfaces, then we don't, this one here at the top, these proper no tension interfaces, I think we're definitely going to see a different pattern in terms of the collapse mechanism. And I'm pretty sure that we are going to see a pretty substantial decrease in limit load as well. So we had about 2,300 here without interfaces, without no tension interfaces, so with full tension at the interface. And I think we should see a pretty dramatic drop in the capacity as a result of actually having the interfaces. Yeah, so already at 1,400, so about half. Yeah, so we have this gap opening up here, which is really kind of what we would expect. And yeah, so capacity, it's a little over half of the other one, but really quite a different mechanism. The soil is only activated really at the front of the anchor. Yeah, like that. So it looks a lot more reasonable and a much lower capacity than this situation here, right? So that's how that is. So yes, suction anchors can be modeled really quite easily. And yeah, just final comment. If you wanted to sort of experiment with the optimal location of the force application point, it is actually possible to move this point. So it is at a coordinate of, the Z coordinate is 8 here. So if we wanted to move it up, we could move it up to 0.9. And then it looks like that. So yeah, I think that's it. So thanks again for joining in, and hope you have a good holiday, and hope to see you again in the new year.
Yeah, thanks for that, Kristian. Very, very nice, and a lot of stuff in a short time. So very, very impressive, I think. Kristian, could you just before I forgot one thing in the beginning. Could you just bring the web page back?
Sure.
So and go to the front page. So this is today's webinar is done, and then early next year we have a lot of interesting webinars. The first one I think will be on the new plate program. So be sure to join that if you like. And as Kristian said, we will have much more webinars coming, not at least on scripting in G3. This is a really powerful thing, and so we hope to have that ready for you in the beginning of the next year. Okay, but thanks for joining in, and have a great holiday and or Merry Christmas for those of you who have celebrate Christmas, and see you next year for a new interesting Optum stuff, I believe.
Yes.
Yeah.
Yes. Thanks for this year, and see you next year.
Yeah. Cheers. Bye bye.